Alright, so you might know how to find the first derivative, but do you actually know what it means? First derivative isn't just some random calculations, they actually help you understand the behavior of a curve, whether it's growing or increasing, whether it's shrinking or decreasing, or whether it's changing direction. That's your stationary points. After this video, you're going to be an absolute pro on first derivatives. The title for this video today is First Derivative Increasing and Decreasing Curves. So let's really understand what the first derivative is all about, because later on we're going to be exploring second derivative, which has its own meaning. So to put it very simply, the first derivative is this function that gives you the gradient of the tangent. It doesn't just give you the sign, it also gives you its magnitude. So whether it's very steep or not steep at all. So if I look at this diagram over here, you can see that the first major points I've labeled are the stationary points. This is where the gradient of the tangent m is equal to 0. So that is how we define stationary points, where the gradient of the tangent is flat, and then later on we're going to explore the three different types of stationary points. We have the minimum, the maximum, and the horizontal point of inflection. Now, if I look at the other parts of the graph, you're going to notice that this portion over here, if I were to imagine drawing tangents all along it between those two x values, it doesn't really matter that some are steeper than others, they're all negative. So the terminology we use, we say that this portion is decreasing. That makes a lot of sense because if this graph was representing like a population or something like that, you can see over time, the population is decreasing. If you look at the other portions, you can see that the gradients are positive, so that means that the curve is increasing. So this terminology of increasing, it simply just means what is the gradient of the tangent. So if f dash x is greater than 0, the gradient is increasing, it looks like this. If f dash x is less than 0, the graph is decreasing, it looks like this. And if f dash x is equal to 0, the graph has a stationary point, which means that the gradient of the tangent is 0, and it could be one of these three options. Okay. If you want to have a deeper understanding, please watch the video on stationary points and how you can determine their nature. Now, sometimes you're going to get a curve that is referred to as being monotonic increasing or monotonic decreasing. Now, if I look at that word monotonic, mono is one, tonic is tone. So if a curve has only one tone and it's increasing, it means that for all values of x, the curve has a positive gradient. So if I look at this curve over here, you might notice it's a log graph. If I were to draw all the tangents along it, you can see all of them are positive. So therefore we say this is monotonic increasing for all x. If I look at this curve over here, we have a hyperbola. You can see that it's all negative gradients. So we say that this is monotonic decreasing, always decreasing for all values of x. All right, and that's basically it for the content. Let's jump straight to the checkpoint questions. Example 1, in the diagram below, label the points where f dash x is greater than 0, f dash x is less than 0, and f dash x is equal to 0. Okay, so first of all, I need to look for where does it have a positive tangent. So let's just start from left to right. I can see this one over here. If I were to draw a gradient at that point, that is positive, so A. B is going to be a 0 gradient, so that's going to go to C. C is going to be a negative gradient, that goes to B. D, now if you look here, that's actually going to be a horizontal point of inflection. So that's going to be another stationary point. E is going to be negative once again. F is another stationary point. G is increasing. H is another stationary point, and I is increasing. Okay, lovely. Next, example 2. Find the domain over which the function f of x equals to negative 2x squared plus 8x minus 2 is increasing. So you want to get into the habit of anytime you notice the terminology of decreasing or increasing, translate that into maths. So increasing simply just means that the gradient of the tangent, or f dash x, is greater than 0. So if I want to satisfy this condition, what I'm going to do first is I'm going to find out what the first derivative is, and then whatever that is, I'm going to let it be greater than 0. Okay, so first of all, if I differentiate this over here, we're going to get negative 4x plus 8. And then now, since I'm looking for where it's increasing, I'm going to let that be greater than 0. So we get negative 4x plus 8 is greater than 0. Negative 4x is greater than negative 8. And when I divide both sides by negative 4, that flips the sign and we get x is less than positive 2. So that is where the curve is increasing. Now let's also just have a deep understanding of what this means. So I'm going to bring up Desmos. Now, if you don't use Desmos, I highly urge you to get used to using it. It is a fantastic graphing calculator. I use it all the time. I use it not because the question requires me to have a curve, like sketch a curve. It's more of just to like deepen my understanding of the math. So if I wanted to draw up the function in the problem, the parabola, super easy to use. You just need to type it up into this little bar over here. You can see that we've drawn up this curve. Now, if I were to tap onto that coordinate where we have the stationary point, okay, so if I look at that stationary point, that's at 2, 6. You can see to the left of x equals to 2, so that's when x is less than 2, the curve is increasing, isn't it? But if you look to the right of 2, that's x is greater than 2, the curve is decreasing. So you can see that actually fully aligns with our solution over here. So if you want to confirm your answer, then just pop the equation onto Desmos and see if it's correct. Example 3, find the domain over which the function f of x equals to this is decreasing. So I want you to pause the video and have a go yourself. What does it mean for a curve to be decreasing? Okay, so I'm going to now answer this. If the curve is decreasing, it means that the gradient of the tangent is less than 0. So what we're going to do is find the first derivative. That's going to be 10x plus 12. And then now we're going to let that be less than 0. So we get 10x plus 12 is less than 0. 10x is less than negative 12, or x is less than negative 12 on 10, which simplifies to become x is less than negative 6 on 5. Great. Example 4. For what values of x is the function f of x equal to x cubed plus 6x squared decreasing? So it seems like it's the same problem, but this one's going to be a little bit more tricky. First, we're going to start with recognizing that f dash x, if it's decreasing, is less than 0. So if I find my first derivative, we're going to get 3x squared plus 12x. Now, if I let this be less than 0, we're going to end up with 3x squared plus 12x is less than 0. Now, this is interesting because you can see here it's not a linear inequality where you can just make x the subject. It's a quadratic inequality. So what we're going to have to do is whenever you're given a quadratic inequality, you actually want to factorize it as the very first step so that you can sketch out the curve. So if I factorize this, we get 3x bracket x plus 4. Okay, now don't get rid of the 3x. You want to have it fully factored with the two x's. And then this tells me that I'm going to have a parabola with x-intercepts at 0 and negative 4. And it's going to be a concave up parabola because it's positive x squared. Okay, now the reason why you need to draw out your little scenario, it doesn't have to be perfect. It just needs to have the x-intercepts and then the correct concavity. But the purpose of drawing it is to determine the direction of the inequality sign, because this here is like the thing that students kind of struggle with figuring out which one's the right way. So I'm looking for where is the parabola less than 0. Less than 0 means that that y is less than 0. So the portion that is below the x-axis. And that is going to be this region right over here. So these x values is our answer. So that means where x is between negative 4 and 0. So therefore, when x is between negative 4 and 0. Example 5, find all stationary points on the curve f of x equals to this. So if you want to find a stationary point mathematically, that means that the first derivative is equal to 0. So let's go ahead and find the first derivative. That's going to be 6x squared minus 18x plus 12. And then now I'm going to let that equal to 0. We get 6x squared minus 18x plus 12 equals to 0. Now you want to factorize this, but notice how everything is divisible by 6. So if I divide everything on both sides of the equation by 6, we get x squared minus 3x plus 2 equals to 0. And that's much easier to factorize. So now my two factors are going to be negative 2 minus 1. So therefore, x equals to 1 and positive 2. Now, these two x values give you your stationary point, but I want to emphasize that word, stationary point. So that means we need our y coordinate to complete the whole xy point. So just on the side here, I'm going to substitute each of these x values into the original function because the original function spits out the y coordinate. So that's really important. If you plug it back into the original equation, not the original equation, if you plug in these x values into the first derivative, since they're your stationary points, you're going to get f dash is 0 because that's what the first derivative gives you. It gives you the gradient. But if you're looking for the y coordinate, you need to make sure you plug it into the original equation because that's the purpose of the original. So now I'm going to substitute x equals to 1 and 2 into f of x. So f of 1 is going to be 2 times 1 minus 9 plus 12 minus 4. We're going to get f of 1 equals to 1. And now f of 2 is going to be 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 minus 4, which is 0. So therefore, we get 1, 1 and 2, 0 are our stationary points. Lovely. Example 6. Differentiate f of x equals to 2x minus 1 to the power of 4, then evaluate f dash of 0 to determine whether the curve is increasing, decreasing, or stationary at x equals to 0. So what we're going to do is we're going to differentiate this, and then we're going to evaluate f dash 0, which essentially just means you're subbing x equals to 0 into the first derivative. And then when we find that value, we're going to determine is it positive, is it negative, or is it 0? And then hence determine whether it's increasing, decreasing, or stationary at that point. All right, so first let's find the first derivative. If I differentiate this, it looks like we have to use chain rule. So I'm going to bring the power down, reduce it by 1, and times it by the derivative of the inside. So we end up with 8 bracket 2x minus 1 cubed. Okay, lovely. Now I need to sub in f dash of 0. So I'm going to sub in x equals to 0. We get f dash of 0 equals to 8 times 2 times 0 is just 0. So 0 minus 1 is negative 1 to the power of 3. Negative 1 cubed is just negative 1. So that becomes negative 8. So therefore this is less than 0. So therefore it is decreasing at this point. Great. Example 7. Show that the function y is equal to negative 3 on x is monotonic increasing. If something is monotonic increasing, it means that the gradient of the tangent is always positive. So there are a few ways to show this. Now first, let's make sense of this. If I wanted to draw this curve, what would it look like? It would be a hyperbola, right? So if I wanted to draw in that hyperbola, normally hyperbolas in the form of y is equal to 1 on x looks like this. If I have a negative, it's going to switch the quadrant. So it's actually going to be here. Okay, now first confirm, is this curve always monotonic increasing? Yes, it is. It always has a positive gradient. Cool. So that's graphically, you can see why it is, but that's not enough to show. So we have to do a little bit of like mathematical working out. So what I'm going to do is I'm going to find the first derivative. So I'm going to bring x to the numerator just to make it easier to differentiate. Y dash is going to be negative 3 times negative 1 is positive 3, x to the power of negative 2, or y dash is equal to 3 over x squared. Now, if I look at this first derivative, I want you to notice the different parts of it. So we have a positive number in the numerator, and then the denominator, you have x squared. What's interesting about x squared? Regardless of what x value you plug into here, whether it's positive or negative, it is always going to spit out a positive value. Now, the only value that it can't take is 0 because you can't divide by 0. So I'm going to say here that x squared is going to be positive always. For all x cannot be 0. Okay, so it's always positive. And then you got the numerator is always positive. When you have a positive divided by a positive, that's always positive. So therefore, you can say that y dash is greater than 0 for all x cannot be 0. And that's it. Example 9. The curve y is equal to x to the 5 plus mx cubed minus 2x squared plus 5 has a stationary point at x equals to negative 1, find the value of m. Okay, so we know that this curve, which has an unknown m within it, has a stationary point at x equals to -1. If I were to translate that mathematically, it would mean f dash of -1 is equal to 0. Or if I plug in x equals to -1, it spits out f dash is 0. Perfect. So what I'm going to do is I'm going to find the derivative of this guy. 5x to the 4 plus 3mx squared minus 4x. And then we're going to substitute when x equals to -1, y dash is 0. So we get 0 equals to 5 times -1 to the 4 plus 3m times -1 squared minus 4 times -1. So this becomes positive 5 plus 3m plus 4, which gets 9 plus 3m. 3m equals to -9, or m equals to -3. So this is going to be the coefficient of x cubed such that we have a stationary point at x equals to -1. And then let me just quickly plug them to decimal so you can see why. Okay, so if I plug in the equation with the known value of m, which is -3, you can see here that we do indeed have a stationary point. We do have a stationary point at x equals to -1, which happens to have a y coordinate of 5. Cool beans. All right, so that is it. I've done all sorts of questions related to the first derivative and increasing and decreasing curves. I hope you guys enjoyed that video and you are feeling more confident than ever to tackle those exercise problems. Thank you for joining, and I'll see you guys in the next video. Bye.